Hello everyone, and welcome back to Lecture 9 of our introductory course to quantum computing. In this lecture and in the final lecture, we'll be talking about how quantum computing is applied and how research on quantum computing is progressing throughout the world. With that being said, let's dive into some of the applications of quantum computing. However, just one quick disclaimer before we get into this lecture. The applications of quantum computing have not fully been discovered yet, and a lot of what I will be talking about in this lecture will be applications of quantum computing that are predicted and have been experimented with, and these applications are predicted to be very good for quantum computers, yet not everything is set in stone, and there could be more applications in the future, or one of these applications may not be very effective in the future, as more research on quantum computing is conducted. So the first application of quantum computing that we'll take a look at today is quantum computing's application in quantum chemistry and drug development. Quantum computing is very good at simulating molecules and atoms, as much of quantum computing is based on them and other quantum mechanical phenomena. As a result, there are a lot of applications of quantum computing in developing cures for diseases and creating more efficient fertilizers for crops. Essentially, quantum computing is very good at simulating nature because a lot of its operations are based off of nature. And as a result, it can perform these simulations of nature much faster than classical computers, allowing it to perform much better than classical computers in these fields. Second, we'll take a look at quantum computing's application in optimization. So, quantum computing excels at processing a large amount of information because of the three quantum mechanical phenomena that we've talked about: superposition, entanglement, and interference. As a result, it also happens to be very good at optimization. Some specific applications of optimization include the supply chain and trucking routes, and one problem in specific that researchers are looking at is the traveling salesman problem, which I encourage you to research as well. However, optimization is a very broad term, and in a lot of the following applications, we'll sort of see evidence of optimization in these applications as well. So this optimization is more of just an optimization in the supply chain and also trucking routes as well. Now we'll take a look at quantum computing's application in machine learning. So neural networks and quantum computing are connected, and researchers are developing these quantum neural networks, or QNNs, compared to classical neural networks, CNNs. So some of these quantum neural networks that they're working on are quantum perceptron models, quantum neural networks, quantum convolutional neural networks, and dissipative neural networks. And similar to classical machine learning, we can train quantum circuits to be used in some of the other fields mentioned before, like quantum chemistry and drug development, as well as optimization. So, just like with optimization, a lot of our applications of quantum computing can also be applied to quantum computing's other applications, so they sort of overlap a lot. Now we'll take a look at quantum computing's application in finance. Because quantum computing is very good at processing large amounts of data, as we stated earlier, and this is due to the three quantum mechanical phenomena that it takes advantage of, which are interference, superposition, and entanglement. So because it is good at processing large amounts of information, quantum computing has many use cases in finances. These include evaluating risk, whether it be in the stock market or of investment opportunities, forecasting markets and future prices, and overall, just being able to make faster and more accurate decisions compared to classical machine learning, and just classical computers in general. Now, a recent term that has sort of popped up that quantum computing has many applications in are smart cities. So currently, there are a lot of cities which use classical machines in order to optimize a lot of their systems. However, a lot of the smart cities have a lot of information to process, and as a result, quantum computing has many applications in smart cities and just running smart cities. So in 2019, Ford and Microsoft collaborated to find that using quantum computers could reduce traffic congestion in cities by 73% and create an 8% cut in commuting time. Additionally, smart cities could also be used to optimize electrical grids and predict weather and natural disasters more accurately. So as mentioned earlier, cities must process vast amounts of data, and quantum computers happen to be very, very good at this. Quantum computing can also be applied to agriculture, although it's a lesser known use case currently. So as mentioned before, quantum computing can help us create more efficient and healthier fertilizers to stimulate crop growth. So applying quantum computing to drug development also in the process indirectly applies quantum computing to agriculture and helps agriculture as well. Additionally, quantum computing has the possibility of helping us identify which genes amplify the best qualities of crops, which will help us produce the best crops, allowing us to optimize the genes in our crops. Finally, we could also use quantum computing to develop more efficient ways to manage our crops, including how we prescribe water and nutrients to our crops. And this is something that I've been working on through my project Quantum Mind. And you can take a look at my work and my research through the website that'll be located in the resources tab on the course. Cryptography also has its application on quantum computing. So much of today's RSA encryption and encryption in general is based on factoring large numbers in order to get back a key. However, Shor's algorithm, which is a quantum algorithm created by Peter Shor, has the capability of factoring large numbers extremely quickly compared to our classical systems, which could shatter our current encryption. So what may take thousands of years for a classical computer to decrypt might only take a couple minutes or a couple hours for a quantum computer to decrypt. As a result, we have a lot of post-quantum encryption techniques being researched. I think the main one that I know is lattice-based encryption. Additionally, there's something called the BB84 protocol, and this is a protocol which lets two users know whether someone is eavesdropping on a secret conversation based on a given key. So we can see that quantum computing has many applications in cryptography. The final application of quantum computing we'll take a look at is the application of quantum computing in helping the environment and reducing climate change. So one of the main applications of quantum computing in the environment is that quantum computing can help us find new ways to sequester carbon from the air, which will remove it from the air and decrease the amount of greenhouse gases within our atmosphere. So this could greatly reduce the amount of global warming that we're undergoing on our planet. Additionally, quantum computing could help simulate wind flow in order to optimize wind turbine placement to increase wind energy production, which obviously increasing our renewable energy production could shift away our reliance on our fossil fuels and overall reduce pollution and help the environment. So that's it for today's lecture. In our final lecture, we'll be talking about the quantum future, including some of the companies in quantum computing, how the US is taking its approach on quantum computing, and finally, how the quantum education looks and how you can get it further into quantum computing. See you then.